All right, I'm a couple minutes late because I was preparing for class and I came across something which is kind of mind-blowing, which I'll show you in a second. So we were talking about how we do linear regression, and then we discussed the process of how we can use linear regression in the context of certain nonlinear data. So basically exponentials and power functions and things like that. And what we'll continue on today is how to do polynomial regression, which you'll see in a second. But this is what, this was in my class notes. I was teaching the same class, actually in the same room, so this is kind of creepy, in the same room last spring semester. And of course, we all know what happened last spring semester. And so it was around this time when we were talking about curve fitting and regression analysis that, of course, the coronavirus was starting to rear its ugly head. So at this time last year, so middle to end of February, it was still being thought of as a primarily China event. Everyone around the world was worried about it, but we really had no idea what was going to happen at the time. This is an article from February 17th of last year, so almost exactly a year ago. I'd stuck it in my notes for the linear regression because it has to do with linear regression. So the title, you can see it there. So the title of it is China's coronavirus data looks too good to be true. Now, Barron's, which is where this appeared, is a financial magazine or newspaper. So they were concerned about economic consequences. But the articles, it's very short, but it's very interesting. So basically, they were monitoring the data coming out of China, just like we still are now a year later. Every day, you know, if you look at the Johns Hopkins site, or New York Times has their own version of it, but Johns Hopkins are the ones that everyone is following. It shows how many new cases per day, how many new deaths per day in every country. It even breaks it down by state and county, in fact. So we've been tracking these numbers for obvious reasons for the last year. At the time, all we had to go on, so a year ago, was what China was telling the WHO, the World Health Organization. So the point of the article is, if you did a statistical analysis or a regression analysis on the data that was coming out of China, both the case data and the mortality, so the death data, the numbers were actually too good. So if you remember last time, we talked about a measure, a quantifiable measure of how good or bad a regression analysis is. It's the R, the correlation coefficient, the cross correlation coefficient. And so interestingly, normally, of course, we want that to be good. And I said last time, I said on Thursday, I said, typically we like that to be in the upper 90%, so up 97, 98, 99%. However, when it comes to health data, when it has to do with human beings or any animal species for that matter, usually the data is very choppy. It's not at all smooth. And you do not expect actually an R value of very large. In fact, in this article, there's a biostatistician who says that normally she's happy with a R value of 0.7. And that's typical of data from human sources or, again, from animal species. So the point of the article was that the data that was coming out every day from China was so good, the R value was like 0.99, which again, in most contexts, we say, oh, well, that's great. But in this context, what that told the experts was, there's no way, you can't trust these numbers. So their conclusion was they were not reporting actual cases and deaths. They were reporting numbers that were predicted from a mathematical model, which of course would be smooth. So they talk about the exponential rise, and you can find these models online. They're actually pretty simple They're just ODEs. They're called SIR models. S and I and R stand for something. And you see people talk about this exponential rise that we saw last March and April. And then we in this country saw again in the summer, and then pretty much most of the world saw again in the fall. But the point was, the data was just too good. It fit that exponential curve too well. And it's true, if you look at all the data we have now in this country or anywhere, it's very choppy. So overall, if you smooth it, if you do a curve fit, you can certainly fit a exponential curve to it. But if you look at the actual data, it's quite choppy around that exponential. And you would never get an R in the 90%. And that was the point of the article. So it was very interesting. The number of cases that were reported at the time, as of February 17th, 2020, were almost all in China. They reported 60,000 cases up to that point and 1,400 deaths, which sounds kind of quaint, because now, just yesterday, we passed an estimated 500,000, so 500,000 deaths just in the US alone. And the US accounts for, and this has been surprisingly robust. So almost from the very beginning, the US has accounted for roughly a quarter of the cases as well as the deaths in the entire world. And that's for a country with about 5% of the world's population. So we've been disproportionately doing a very lousy job of dealing with the pandemic. Most countries have done far better than us. New Zealand, just 2 weeks ago, they shut down a whole city, Auckland, because they had 3 cases in one family. 3 cases in one family, and they shut down the entire city. They went months, literally months, starting in the summer, where there was not a single new case in the entire country, New Zealand. Now, they have a slight advantage in that they're an island, so it's easier to restrict movement and so forth. But the point being, the US has done a particularly poor job in managing this crisis, and consistently poor throughout. So like I said, if you look back at the data for pretty much the entire last year, we got a little bit of a late start. Italy, China was hit first, then Italy, and then other parts of Western Europe and the US. But since we entered the picture, we have roughly been accounting for a quarter of the cases and deaths, which is just astronomical. And I always remember back in the early part of this, in March last year, when the experts were saying that in this country, we may have upwards of 240,000 cases. And at the time, we were just, our jaws dropped to the floor, because that just seemed astronomical. Just not cases, sorry, deaths. And that just seemed ridiculous. There's no way things could get that bad. And of course, here we are, where we've more than doubled that. And of course, it's still raging. So anyway, this stuff matters. How you do this regression and how you interpret it, what you do with those numbers, it matters. These are very useful skills to have. Okay, so let's continue on with what we started talking about last time, which was, again, regression analysis. So far, we've only looked at linear regression, so assuming things behave as a straight line. And then we said, well, if I have an exponential curve, or I have a power curve, like an x to the something, then I can do a little bit of math, basically take logs of things, and I can reduce that down to a linear regression problem, which we can then solve using the normal equations for linear regression, get the solution, and then we're good to go. And we did an example last time. So we started with a set of data, X and Y data. In this case, only at 4 points, because we're doing it by hand. So 4 points, X and Y values, and we wanted to find the A0 and A1 coefficients, constants, in this power function. And by taking the natural log of both sides, you can reduce this down to a linear regression problem. And then we solve that linear regression problem, and we get the values of the constants, map them back to the A's from the C's, and then we have our function, trial function, which approximates that data. Okay, so next we want to look at polynomial regression. Obviously, not all curves are going to map nicely or be dealt with nicely using lines, straight lines, or exponentials or power functions. So we need some more general regression techniques as well. So polynomial regression is an extension of linear regression. Linear regression is a special case of polynomial regression, as you'll see. And it'll basically just be more of the same. So we'll be doing the same approach, just with more constants. So let's take a case here. We have 10 points, so capital N is equal to 10. And you can see they're clearly not a straight line. So a straight line curve fit would be lousy. An exponential curve fit would also be pretty poor. So we need something better that we can use. So if you look at this, you say, well, it kind of looks like a cubic polynomial, of order 3 polynomial. So that's what we're actually going to do. We'll do a cubic curve fit on this, but I'll set up the math for a general polynomial, and then we'll set m is equal to 3 and determine the curve fit for that data. So let's put that data aside, but kind of keep it in mind as we walk through the process. The process is exactly the same as before. So we define the residual, which is the difference between the values of y for the data points. So each data point has xi, yi values, and then there are n of those data points. So those values we know, xi and yi we know. So the residual is the difference between the value of yi for a given point, the ith point, and the value of f of x at that same point, xi. That difference is the residual. So if you remember from last time, it was a straight line, f of x was a straight line, and then we had points like this. So this was like x, I, y, I, and then this was the residual ri. So it's the distance from the f of x curve to the actual points. And we have capital N of them. So there's capital N residuals. There's the residual for each of the points. Then we defined a trial function, f of x. Previously, the trial function was a straight line. So it was c0 plus c1x. And now all we're going to do is add some more terms. So we'll add additional integer powers of x. So in addition to 1 and x, we'll have x squared, x cubed, all the way up to x to the power m. So m will be the order of the polynomial, and n is the number of data points. So n, Nancy, is the number of data points. M, Mary, is the order of the polynomial. They're not the same, and they don't necessarily have anything to do with each other. Okay, so now the basis functions before were 1 and x for a linear curve fit. Now it's all the integer powers of x up to the mth power. So again, same idea as before, just more the same. We define the total error in the same way. The total error is the sum of the residual squareds. And remember, we square the residuals because we don't care about the sign. I don't care about whether the point is above the curve or below the curve. I just want to minimize the distance from the curve, whether it's positive or negative, above or below. So we square the residual being y minus f of x. And so again, each point has a residual, so we sum all those up. So in this case now, the f of xi is this new trial function, which is an mth order polynomial. Once again, this is exactly what we had before, but we only had c0 plus c1x. Now we have additional x squared, x cubed, up to xm terms. Following the same steps as before, we're now going to differentiate the total error with respect to each of the unknown constants. Once again, before we just had two, C0 and C1. Now we have capital M of them. And so we're going to differentiate the total error E with respect to each of the constants, C0, C1, C2, C3, C4, all the way up to Cm. And then we set them equal to 0. And that is going to give us a linear system of algebraic equations. Again, just like before, just more unknowns. Instead of 2 unknowns, we'll have capital M unknowns, actual capital M plus 1 unknowns. All right, so we go back here and we have this thing in square brackets, squared. So when I differentiate with respect to these C's, I'm always going to have a 2 times something, 2 times this, and then I'm going to have the derivative with respect to C0, C1, C2, and so on. So for the C0 derivative, I have my 2 times y minus the residual, now to the power 1, because I differentiated, times the derivative with respect to C0, which is minus 1. So that's why we have the minus sign out front. So minus 2 times this. Then you'll notice what happens in each of the successive terms. So when I do now C1, again, it's 2 times the same thing in square brackets. But now, when I differentiate with respect to C1, I get minus x1. So minus, sorry, not x1, but xi. Minus xi. You see the xi here at the end. Then for C2, it's going to be minus xi squared. So minus xi squared. And then all the way down. So each one of these, you can see this is an xi to the 0, xi to the 1, xi squared, xi cubed, to the 4, to the 5, all the way up to m. So the last one is 2, so then minus 2, times the residual, times the derivative of the Cm with respect to Cm, which is that minus there, xi to the power m. Now we know all these. The xi's we know, the yi's we know. So we know everything in here except for the c's. Those are the unknowns. We know everything else. So now we end up with capital M plus 1 linear algebraic equations to solve for the capital M plus 1 unknown coefficients C0 through Cm. So again, think of the linear case where we had M is equal to 1. So we had 2 constants, C0 and C1. Now we have C0 through C sub M. So here's the system of equations that you get. So where does everything come from? These yi's, and here you have a yi times xi, here you have a yi times xi squared. All of those go on the right-hand side because those are all known. So here's the sum of the yi's from that first equation. Here's the sum of the xi's times yi's from the second equation, xi squared times y squared, sorry, times yi's, all the way down to x to the power m times y. Those are all on the right because we know those values. Just get those from our tabulated values. This is my vector of coefficients that I'm looking for. So that's what we're solving for, the C0 through Cm. And then the matrix here is going to be M by M. There's M unknowns, sorry, M plus 1 unknowns, and M plus 1. So it's M plus 1 by M plus 1. M plus 1 unknowns and M plus 1 equations. So now where do these come from? Same as before. So notice this first term, forget about all the minus 2's because we have equals 0, so we can get rid of those. I have the sum of the C naughts. But how many C naughts are there? Well, there's n of them. So it's n times C naught in the first equation. Then this term gives you that's C1 times xi. So now that's a sum of all the xi's times C1. And then the next term is the sum of all the xi squareds. Sum of all the xi squareds times C2. Okay? So once again, it's just a system of equations now, capital M plus 1 equations for capital M plus 1 unknowns. You'll notice if M was equal to 2, sorry, if M was equal to 1, in which case you would have a 2 by 2 system, notice what you get. You get exactly back the normal equations that we had for the linear regression case. So again, this is a generalization of linear regression, or you can think of it as linear regression as a special case of polynomial regression. And you'll see the pattern here. So here you have the sum of the xi's, xi squareds, then the next one will be xi cubes, all the way up to the xi to the power m's, and then they shift by 1. So this is now the sum of the xi's, squareds, cubes to the m plus 1s. And then it's just like the normal equations in the linear case, these are symmetric. This is the same, these are the same, these are the same. So it's symmetric, just like the linear case. Okay, so it's just more of the same. That's all it is. It's just a bigger system of equations to solve. But given the xi, yi data for your capital endpoints, you just fill in the right-hand side vector and this coefficient matrix, and then solve for your constants in the trial function, the C constants in the trial function.
Professor?
So if you do, yes.
I think there's some questions in the chat.
Okay, thank you. Dr. Castle, where does the -2 come from? All right, let's go back and find the -2. So here is, remember the residual is the thing in square brackets, but the error is the residual squared. So when we take the derivative, we get a 2 from here, and then you reduce the power by 1. So it's 2 times the residual. Then from the chain rule, then you differentiate the thing inside the square brackets, in this case with respect to C0. So with respect to C0, the derivative is -1. So that's why you have the minus out front. And so all these minus signs give you these minus signs here. Okay, so that's the -2. Sorry, Professor, you lost me with all these general equations and variables and summations. Could we go over a worked example? Actually, it's exactly the same as this example right here. So in this example, we turned this nonlinear power function into a linear regression. The only difference now for polynomial is rather than just C0 plus C1x, I now have a C2 times x squared plus C3 times x cubed and so forth. Everything else is the same. So again, you'll notice this 2 by 2 matrix here, and this right-hand side is exactly the same as this one right here and right here. They're exactly the same. So it's just more of the same. It's exactly the same process as in that last example. Okay, so when you do that for this original data that we started with here, these 10 points, and you can try it. You can try linear and you can say, okay, well, linear is not so great. Let me try quadratic. A quadratic is a polynomial. If you do a polynomial, that's gonna be terrible. So then you try cubic, so third order, and that turns out to be pretty good. And you can go higher if you want, but generally you want the lowest order polynomial that does a decent job with a particular data. So in this case, a cubic works pretty well. And so you can see that here. So here is what you get from the regression analysis. That's the solution for this is C0, C1, C2, and C3. And so that then is this solid line. And you can see it does a pretty good job of fitting to the data itself. There's also example, yeah, go ahead. Yeah, so that's a good question. So the question is, are we just guessing? So you're given the n, right? So the number of points you're given. And then the question is, are we just guessing the m? And the answer, unfortunately, is kind of yeah. So we're using our intuition and our engineering judgment in the sense that, like I said, if I try this, and it's easy to do, it's just put in the machinery and have Python or MATLAB do it. You can get the straight line. You can see, oh, well, that's not very good. And you can get the R value and find, well, that's not that great. Clearly, it's not a parabolic. It's not a quadratic. Third order does well. Fourth order would do even better. Fifth order would do even better. So there's a trade-off between the higher order of the polynomial, the better the fit's going to be. In fact, for interpolation, which we'll discuss in a few minutes, if I were to use, because this is n is equal to 10, if I were to use a 9th order polynomial, I could get a polynomial that exactly goes through every single one of these points. So for 10 points, I could choose anywhere but m is equal to 1 up to 9, basically. And it's up to me. It's my engineering judgment that determines which one is best. So it's not a guess, but it is. There's no formal guidance as to what to pick. Now, that leads into another question, which is an excellent one, is how do you choose it? So that gets you into neural nets and machine learning. So what machine learning does is it gives you, which it's beyond our the topics in this class, but machine learning would give you a way to determine what is the best set of basis functions. So if it's a polynomial, what order polynomial? Or maybe it's not even a polynomial. We'll look at some Fourier analysis a little later, probably on Thursday, where it's sines and cosines, and maybe that works better. So you can use, and there are methods in machine learning and neural networks that allow you to, or give you the capability to determine what is the best trial function. But for our purposes, it's basically plug and chug. So once you decide what m is, then it's just plug and chug to get the values of the c's. And then it's your judgment. And you get the answer and you say, well, yeah, that's a pretty good fit. Or no, it's not good enough. So let me go to a higher order. And that's kind of the nature of the beast, unless, like I said, you get into the machine learning, neural network sort of approaches that go beyond just the basic regression analysis. Good question, and a very important one. Okay, so clearly the trade-off then is, as I said, I could, for my n is equal to 10 data, I could pick m is equal to 9, and I could have my polynomial go through every single one of those points. Or I can have a lower order polynomial and say, well, that's good enough. Well, what's the trade-off? The trade-off is the larger m is, the larger the system of equations I have to solve. What if m is 1,000? What if m is 1,000,000? I don't want to solve 1,000,000 coefficients in a 1,000,000th order polynomial, nor do I want to do it, but also it creates some problems, which I'll illustrate in a couple slides. So there is, again, this trade-off. I want to get the answer quickly. I don't want the problem to be too big. So I want to pick a low order polynomial, but I want it to be a sufficiently good representation, curve fit of the data. So as I've said, linear regression is just a special case of this when capital M is equal to 1. So now you have two unknowns. It's capital M plus 1. And you can do that for any set of data. Again, it's just a matter of whether it's good or bad. Polynomial regression is where m, excuse me, is less than n minus 1. Of course, n being the number of points. If m is equal to n minus 1, then that's polynomial interpolation. And again, the main difference is, the big difference, fundamental difference is, regression analysis is a curve fit. So the curve does not go through the points necessarily, unless they just so happen to be on the curve, like the example we did last Thursday. But in general, they won't be. Interpolation, the curve does go through every single point. So it's a fundamental difference in the purpose of what we're trying to do. And we'll discuss that more in a moment when we discuss interpolation. But in any case, we have all the possibilities with polynomial regression. Linear, m is equal to 1. m is somewhere between 1 and capital N minus 1, that's polynomial regression. And when m is equal to capital N minus 1, that's polynomial interpolation. The way you do this in MATLAB, there's a polyfit for polygon fit. You input a vector x, which is all the values of the x coordinates. So that's xi, 1 through n. The corresponding values of y, another vector. So that's all the y coordinates, 1 through n. Then you put in the order of the polynomial that you want. So the m order polynomial, the degree of the polynomial. And then it returns p. So you get back p, and the p that you get back is all the coefficients. They are, note that they're in the order from the highest order power of x to the lowest order. That's different than Python. So Python starts from 0th order, goes up to the nth order. MATLAB starts with the nth order and goes down to the 0th order. So just keep that in mind. There's a slight difference there. So you put in the x and y values, tell it what order polynomial you want, and it returns the coefficients in that polynomial from the highest degree to the lowest degree. In Python, it's quite similar. You can actually put in any trial function that you want. So you define your trial function, use the define function to define your trial function. In this case, you're indicating the independent variable and whatever constants are in there. If it's polynomial regression, then you would have C0 through Cm. I've just done the example here of linear regression. And then you explicitly put in the trial function itself. And this can be anything. So here it's a straight line. You could add, plus C2 times x squared plus C3 times x cubed, and then you have a cubic polynomial. Or you could put in an exponential or anything else you want, any other function you want. Then you call curve fit. You pass the trial function, which you just defined. You have your x and y vectors, just like MATLAB. Those are the x coordinates and the y coordinates of the data point. So those would be vectors of length n. There's also this P0 argument that you pass. It's the initial values of coefficients in the trial function. That just sets the size. So you just put 0, 0 there for linear regression. And then the coefficients are what you get back. So you get back the vector of coefficients in the trial function, again, starting now from C0 up to Cm instead of the other way around, like in MATLAB. And then it also returns the covariance matrix, which we don't need for our purposes, but it does return that if you need to use that for some sort of future processing. But for our purposes, you can just ignore that. It's just the coefficients that we care about. And as with all of these operations, there are examples in the Python tutorial on Blackboard. So you can use those, copy and paste them, and modify them accordingly for the problems that you're trying to solve. Okay, so that's polynomial regression. Oh, I love these. Since you're not PhD students, you probably don't follow PhD comics. However, you should, because they're funny, even if you're not a PhD student. The reason why they're called PhD comics is the guy, Jorge Com, who started these years ago, was a PhD student, and he was bored, I guess. He wasn't accomplishing much research, so he started these cartoons. He's actually had a few little short movies based on some of these characters, and some of them are really quite funny, and most don't really have anything to do with being a PhD student necessarily, but generally academic environments. So this one's kind of funny. This is for programming for non-programmers. Here's your generic student. Here's your generic professor. And you can see the code up here, the lines of code in all caps. So include limited programming skills. So the student, starts out the project, has really no idea what to do. The boss, the professor says, what the deadline is. And of course, it's always in the past. Load code by previous person on project. So this is why I'm showing this one. There's a moral to this story. So I'll go through it, but then I'll get to the moral of the story in a second. So you find the code that the previous student on the project was using, which of course is a huge mess. While project not finished, input random typing, set self-esteem to low. For time equals infinity, debug, debug, debug. You can see the coffee cups here that are continuously feeding our student. If the code works, euphoria, set self-esteem above normal. If not, organize and comment code for next person on the project. The moral of the story is this. One of the most difficult aspects of coding is trying to figure out what someone else has done. When you write your own code, and I actually like looking at students' codes because everyone's different. There's actually quite a bit of room for creativity in coding. Most students think, oh, coding is just kind of this boring, tedious, rote sort of process. But there's actually quite a bit of room for creativity in how you do your code and how you set it up, how you comment it, how you conduct the steps in the algorithm and so forth. The problem is, because everyone's code is so individual, when someone else looks at your code later on, it's often hard to figure out what you were doing because you inevitably don't do it the same way that the person who's looking at it would have. And so this is why it's so important to comment your code. And it often seems like and feels like a waste of time writing comments, but the more detailed the comments are, the more likely it is that someone else can decipher your code and figure out what you were doing, or even you. It's amazing how quickly you forget what you were doing specifically in a code. And the other thing is it helps debugging. So if you code in a good modular fashion, have lots of little functions that do just one thing, it makes it easier to debug. And so the debugging process is a big part of this. But anyway, so oftentimes we're not writing new codes from scratch. We are trying to figure out what someone else's code was supposed to do and either improve on it or add some new features. And of course, to do so, you have to understand what they were doing. So that's oftentimes one of the most difficult aspects of coding for any of us, and that never goes away. But on the other hand, looking at other people's codes gives you ideas, because sometimes you never would have thought to do something in the way they did. And so that can also be kind of helpful and a healthy thing as well. Okay, any questions about polynomial regression or curve fitting in general before we move on to interpolation? So again, the point of curve fitting is you're given some data, a bunch of x, y values, so inputs x's and outputs is y's is. And no, I don't normally talk like that. I blame it on Lord of the Rings, you know, the character Gollum, who kind of has a lisp. So that's my mathy Gollum imitation. Anyway, that's neither here nor there. So the point of curve fitting is you have inputs x, which are your independent variables, you have outputs y, which are your dependent variables, and you want to fit a curve to it for some reason. You want to represent the curve, you know, the number of cases of coronavirus in Chicago over time. You want to represent it as a curve so you can do some analysis on it, so you can better understand it, so you can see when the cases go up or down based on decisions that the mayor and the governor make and so forth. So curve fitting is finding a best fit curve, such as a line or polynomial through the data. Interpolation has a fundamentally different purpose. It's the same, it's very similar mathematically. In fact, it's exactly the same analysis as I've already alluded to, but it's for a different purpose. The purpose of interpolation is to be able to get values or estimates of values between data points. So one of the examples or one of the problems I have you do in the problem set 3 is we have population data given for the world at various decades, you know, so 1970, 1980, 1990, and so forth. And then the question is, well, estimate the population in some year, estimate the population in 2007, or, you know, whatever year you pick. So the point of interpolation then is to come up with a way or have a way to formally estimate the values of y at points between the x's. So in other words, you have the values of yi at the xi's for your endpoints. That's fine. So if you want the value of y at one of those xi's, then you just take the appropriate corresponding value of y. But what happens when you want a value of y between the xi's? So that's interpolation. Generally speaking, as we've said last time, curve fitting is used when the data isn't that great. So there looks like, or we know there's a lot of error or noise in the data. Interpolation is generally used when the data is very good. So if you've taken a class like 320, the thermodynamics course, and you need values of enthalpy or pressure or temperature or whatever, and you go in the tables in the back of the book, and you end up doing a lot of interpolation, right? But the values in the back of the book are very good. They're very accurate. The problem is you often want the values of enthalpy and so on at points at values between what's given in the table. So you use interpolation to get those. So this is really just a generalization of that basic process. So polynomial interpolation, I don't have to give you any new math because it's exactly the same process as we did for polynomial regression. The only difference now is the value of m, the polynomial that we're using for the fit, is now equal to capital N minus 1. So for our 10 points, we would use a 9th order polynomial, which has 10 unknowns. The resulting polynomial interpolant would go through all 10 points. And I'll show you an example of that in a moment. So that's, again, no new machinery. Solve your system of equations for the C coefficients. And now we call it interpolation instead of regression. That's the only difference, is just what we call it. And again, the purpose for doing it. So I said this, again, it's preferred when you have accurate data and you need to estimate the values between the data points. So the basic problem with polynomial interpolation is that you often get highly oscillatory polynomials. And I'll show you an example of this here in this figure. So this is the same n is equal to 10 data. So this is the same n is equal to 10 data points that we had in the previous case where we used a cubic polynomial. But now I have done interpolation. So instead of fitting a m is equal to 2, I've fit an m is equal to 9 order polynomial. So rather than getting our nice smooth cubic polynomial, now we get a 9th order polynomial. Of course, the higher order polynomial, the more wiggly it becomes. But you'll notice two things. First of all, as we said for interpolation, it now goes through every single data point. So if I put in x is equal to 6, I will get back the corresponding value of y that was in the original data. And likewise for all of the other points as well. So that's the first thing. So there's no more curve fitting. It's no longer a best fit curve. It's now a curve that goes through all the points. But the other thing you'll notice is now where the problem arises. And you can see, particularly at the ends, you get this overshoot. So these 2 points, what I'd like to see is something that goes smoothly like this. But instead, you get this massive overshoot. And that's simply because you have a higher order polynomial. Same thing over here. It's not quite as bad, but you still get this overshoot. There's nothing in the data that suggests that it should look like this. There's nothing in the data that suggests that this should go flying off up to the left like this, or down like this, right? Our cubic polynomial look like this. But for a 9th order polynomial with that particular data, that's what you get. That's the 9th order polynomial that you get. So the higher the degree, so the larger m is, the more likely this is to occur. It'll never happen for a straight line, obviously. For a parabola, it's less likely to happen. For a cubic, it's not likely to happen. But the higher the order of the polynomial, the more likely you are to get these overshoots. So that's an issue that we need to address, and we will address. So I mentioned that. Yep, mentioned that. Yep, mentioned that. So the main issue is then for large n. So again, this is only 10 points. What if n was 100? What if n was 1,000? What if n was 1,000,000? If I were to use a 100th order polynomial, it can be very oscillatory. It'll go through all 100 points precisely, but between the points and beyond the points, it can have all kinds of horrendous oscillatory behavior. So again, there's a trade-off between the size or the order of the polynomial and the corresponding size of the matrix problem we have to solve and how well it fits. We call this overfitting. So we've overfit the data. We've done too good a job in fitting the data. We've done such a good job that it now actually goes through all these points. And the reason why it's bad and overfit is because it ends up with these artifacts which are clearly not accurate or helpful in representing the data. So the answer to this is what's called spline interpolation. So generally speaking, we don't use a polynomial interpolation for n larger than, say, 10. You can already see with 10, we're getting these kinds of issues starting, and it only gets worse as n and m get bigger. It only gets worse. So for n of just a handful, polynomial regression is fine, but for anything larger than that, we go to what's called spline interpolation. So let me describe that to you. So the idea here is rather than having one curve, in this case a polynomial, so rather than having a single curve that goes through all of the data, splines have a low order polynomial, but that just goes through little segments of the data. So instead of having one curve, high order, we're going to have a whole bunch of lower order curves. That's the basic objective. The reason for the name comes from back in the good old days, which actually wasn't that long ago when I was young. Drafts people would use what are called splines to draw curves. So you can see an example of it here. Here is a very thin, it was usually made out of wood, but very, very thin, so it's easily pliable. This one is probably not wood because I don't know if you could get wood to go like that. These are called ducks, like quack, quack. And these are heavy, they're like paperweights. They feel like paperweights. And so you slide them around and you move them around. You can see they've got little hooks that then cause this curve to go in whatever shape you'd like. And the more ducks you use, the closer you can get it to the curve you want. You can see this guy's taken it very seriously. He's climbed up on his draftsman's board and looking very closely. So he's a very dedicated draftsman to get all his ducks in a row. Oh, is that where it came from? Maybe that's where that saying came from. Could it be? So he's literally getting all his ducks in a row to get this curve to exactly align with the shape that he wants. So that's where where the terminology comes from historically. Now, of course, now we have a computer do all the work, and it's systematized. It's an algorithm. It's a process which gives you a unique spline. It's not dependent on who you have do the spline. If each of us in class were asked to make a curve that looks like this, we'll all have a different number of ducks. We'll put them in slightly different positions, and the curve won't be exactly the same. So that's not a very repeatable process. All right, so how does it actually go? Well, the simplest spline you can imagine would be a linear spline. And that's literally just drawing a straight line between every pair of points. So that's a spline. So now rather than having one polynomial, we now have 1, 2, 3, 4, 5, 6, 7, 8, 9 between our 10 points. But they're only order 1. So they're lines, they're straight lines. So that's a linear spline. So that's the simplest possible spline. It's not a great spline. It's easy to construct. It's literally just a straight line between each point, but the slopes don't match. So here, this one and this one, they have different slopes at this point here where they join. So that's not good. The slopes don't match, nor do the curvatures match. So the first derivatives don't match. The second derivatives, which corresponds to curvatures, don't match. So that's not great. A quadratic spline would be quadratics or parabolas between each point. Now, that would give you a little bit more flexibility. You could actually get the slopes to match up at each of the points, but still not the curvatures. So to get the values, obviously we want the values to match up at each point. We'd also like the slopes to be smooth. We would also like the curvatures to be continuous. So for that to be the case, the sweet spot is what's called a cubic spline. So this for the exact same reason as polynomial regression. So lower order doesn't give you enough flexibility. Too high of order, you overfit and you get the oscillatory behavior. So the sweet spot for splines is cubic splines, because the distance between your neighboring x values are generally small. So therefore, you don't need a high order polynomial, but the cubic polynomial will allow for the slopes to be the same and match at each point, as well as the curvatures to match at each point. And that's usually good enough. So a cubic spline, of course, a cubic is a third order polynomial. And so now what we're going to have is a third order polynomial between each point. So it'll look something like this schematically. So if I have a point right here, this is my xi, yi point right here. Okay, so again, these are points that are given to us. These are our data points. Here's the previous point. So that would be xi minus 1, yi minus 1. And then the next point would be, say, here, xi plus 1, yi plus 1. And then one more we'll put here. So that would be xi plus 2, yi plus 2. Now, what we're doing is, between each point, this will be a curve, a polynomial. This will be a separate polynomial. This will be another polynomial. So each pair of points is going to define or bound a polynomial, in this case, a cubic polynomial. So we'll label those like this. So the one to the right of xi, yi will label as f(i)x, f sub I of x. So the previous one would be f sub I minus 1 of x. And the next one would be f sub I plus 1 of x. So these are three different polynomials, fi minus 1, fi, and fi plus 1. And they correspond to the point to the left in terms of the indexing. So the xi, yi point here and the xi plus 1, yi plus 1 point here has the polynomial f sub I x in between. So this I goes with this I. And then the previous one, I minus 1, next one, fi plus 1. All right, so that's the basic setup in terms of the notation. So we're just like before, we're given our xi, yi points at n data points. And we're going to determine each of the fi cubic splines. So if capital N is equal to 10, then we're going to get 9 cubic splines. So again, rather than one high order polynomial, we're going to have a whole bunch of low order polynomials. And that will give us a better interpolant, a better fit. Now, this is that cubic spline. Actually, it's all capital N minus one of them. So here's your fi of x. It has a 0th order term, 1st order term, 2nd order term, and 3rd order term. It's a cubic polynomial. So it has up to order 3. And you see it has these x minus xi's, x minus xi's, x minus xi's. So what's that? Well, that's this. So wherever you are in x between these 2 points, it's x minus xi, x minus xi. So this is a 3rd order polynomial between 2 adjacent points. And then we have capital N minus one of them. So 9 of them for our capital N is equal to 10. All right, now what we need is we need a way to get the A, B, C, and D coefficients. How many of them are there? There's capital N minus one of each. So I have 1, 2, 3, 4 times capital N minus one coefficients to determine. Lots of coefficients, because I need the coefficients. I need the 4 coefficients for each of the capital N minus one cubic polynomials. So I need a bunch of conditions to get those. So I actually need 3. We're going to impose 3 conditions, all 3 of which I've already hinted at. The first one is that 2 neighboring cubic polynomials have to match up at their endpoints. So the endpoints of each successive cubic polynomial have to match. So that means that fi xi is equal to fi minus 1 xi, and that has to equal to yi. All that is saying is, at this point right here, the polynomial to the left and the polynomial to the right have to be such that at xi, they match up. That's all that that's saying. So the 2 polynomials to the left and to the right, actually to the left and to the right, sorry, all have to give the same value yi at the particular xi. Okay, so that's fine. The second requirement is that the first derivatives, in other words, the slopes, have to match. So once again, the slope of this curve to the left and the slope of this curve to the right of our points have
Professor,
to
you
both
have another question in the chat there.
Thank you. So these 2 slopes have to match. So that means that f prime of I, fi prime at xi is equal to fi minus 1 prime at xi. And then the next one, and so forth. And then the third requirement is just the second derivatives have to match. So the second derivatives are the curvatures. So again, curvatures, second derivative, those curvatures match at this point. So the values themselves, the first derivatives are slopes, and the second derivatives are curvatures, all match in the neighboring, for the neighboring curves at each of these data points. Okay, let's see what we got. Can you explain that again? The number 1 condition, sure. So this is given. The value of y, I. So that's this. That's this value. So I know this value, xi, yi, I know that value. My requirement for this cubic and this cubic is that both of them, as they come to the same value of x, so this is xi down here. So for the same value of xi, this curve and this curve give me the same value at the common point. So at the common point, xi, the 2 neighboring curves, fi and fi minus 1, give you the same value. And what is that value? It's the same as yi. And then this is just the same thing at the next point, and then at the next point, and then at the next point. So both ends of my polynomial have to match the values, the slopes, and the curvatures. Does that make sense? Okay. Now, how do you use those conditions? You apply those conditions. And what we want to get are expressions that give us the A, B, C, D. I have done all the math. I've done all the nasty algebra to apply those conditions. Here it is. Write this down really fast. 1, 2, 3, 4, 5 pages of algebra. There it is. Now you know. Obviously, you're not responsible for that. I will show you what it boils down to. So after 5 pages of tedious algebra, applying all of these conditions at every point, you get the following. Remember, what am I looking for? I'm looking for a way to get the A, B, C, and D constants in each of my n-1 cubic polynomials. We'll define the distance between adjacent points as hi. So hi will be xi plus 1 minus xi. So in other words, this is xi plus 1. This distance is hi. And then this one would be hi minus 1. And this one would be hi plus 1. So that's just the notation that we'll use. So hi is xi plus 1 minus xi, just the distance between the x points. They do not have to be the same. So you don't have, your data does not have to be uniformly spaced in x. What you get after the 5 pages of algebra is that your C coefficients have to satisfy this tridiagonal system of equations. So I know all the h's. Those come from the data itself. I know all the y's. That comes from the data itself. The only unknowns are these c's. When you apply this equation for each I, 1 to capital N minus 1, you get a tridiagonal system of equations. Now that sounds familiar. We talked about how to solve tridiagonal systems of equations using the Thomas algorithm. So we have a method to solve this. It's very efficient and very fast. Those two things mean almost the same thing. I solve that tridiagonal system of equations and I get all my C's. I still have the A's, the B's, and the D's, but I've got the C's. Solve a tridiagonal system. Great. To get the A's, D's, and B's, notice the order, they come from, and again, this comes from the 5 pages of algebra. This all comes from the 5 pages of algebra. So once you have all of the C's, you can get your AI's or just the YI's. The DI's are this, CI plus 1 minus CI over 3HI, all of which you know. And then the BI's, once I have the C's and the D's, I can get the B's. That's this, YI plus 1 minus YI over HI minus CI. Why is he talking so fast? Because it doesn't really matter. It's there on the slide for you. So you get your C's first, then your A's, then your D's, and then your B's. Then you know all of your cubic polynomials. Now, obviously, and this is the reason why I didn't do the 5 pages of algebra for you, obviously, we will let the computer do all the hard work for us. So here is that last example. This is with n is equal to 10, those same 10 points, the same one that we did the cubic polynomial for, the same one that I did the linear spline for, straight lines between them. And this is now a cubic spline. And what you'll notice, these are slightly curved, and they're curved such that the slopes and the curvatures are the same. So if I were to differentiate this curve once, it would be smooth. Do it again, second derivative curvatures, it would also be continuous. So that's a cubic spline. And once again, you'll notice there's no issues with overfitting that we saw with the 9th order polynomial at the ends. So this is clearly a better interpolant for those 10 data points than this. right? It's nice and smooth through those points. No overshoots like here, here, and here. And what do I have to do? Well, I have to solve a tridiagonal system of equations. So it's really not much more work. In fact, it's not any more work, but it's a fundamentally different approach to getting those values. Okay, a couple comments. Once again, as I said, the data points do not need to be uniformly spaced. So however they come, that's how they come. So like our population data, maybe you have the population in 1970, in 1985, but then you don't have anything until 2005, and then 2020. That's fine. They don't have to be uniformly spaced. That's fine. We do need additional conditions at the endpoints, because if you notice, if you think about it, what happens here and here? So I don't have a value to match up to here. I don't have a slope to match up to here. So what do you do for this? Obviously the value has to match this point, but what do you do for the slope and curvature? So there are different types of splines, and I'm not going to get into the details of these. I just kind of want you to know some of their terminology. A very common one is called a natural spline. And what that means is at the endpoints, at the very ends, you have zero curvature. So it's a straight line at the ends. That's a natural spline. Another common one is called not a knot. N-O-T, K-N-O-T. In splines, a K-N-O-T is a point that the spline must pass through. So if you've ever done splines or Bezier curves are splines. It's a form of a spline. And if you've ever done them in software, like in a CAD package, the first and last point, it always gives you this extra point that you can move around. And you can see as you move that point, it changes that last piece of the spline at the two ends. So that is called not a knot. So you have an extra parameter. You can say, well, I want it to come to the endpoints, the two endpoints, but I want it to come to the endpoints such that the slope is going to follow this, and it's going to go through these extra points, these extra knots. So that's another possibility. So in MATLAB, the way you do splines is to use the interp1 function, interp obviously for interpolation. So interp1, the x and y values are the same as before for polyfit. The xi values is another vector. It could be a scalar, but it could also be a vector. Those are the points at which you want the values of y. So say I wanted the population at 3, I wanted it at 1976, 2010, and 2017. So you could put in 3 values into xi, and then it will return 3 values in yi, which will be the values of y that correspond to those 3 values of xi. So it could be a single number, so a scalar or a vector of just one value, or it could be any number of values at which you want the values of y, the interpolants. And then you can specify the method. So you can tell it, for example, that you want to do splines. Now this should be no K here, so sorry about that. This is not a knot. So the default in MATLAB is to use not a knot method at the endpoints. So, but there are different methods you can use. So you can use polynomials, you can use splines, as is here. Typically, splines, the default spline is a cubic spline, although you can tell it to use other splines if you'd like. In Python, it's somewhat similar. So it's interp1d is the name of the function. You put in your x and y vectors or arrays, just like before, the values of x and y that correspond to each other at the data points. You tell it the kind, rather than method, its kind is equal to what you want. So you can put in linear, you can put in cubic to get different types of splines. And then the interp function returns the interpolating function. Now, this is different from MATLAB. MATLAB just gives you the values of y for the values of x that you specified. Python, the interp 1D, it actually gives you an entire function. It returns an object, and that object is the entire function, which is actually kind of nice because then you can do whatever you want with it. Then it's like a straight line or a polynomial or whatever it returns, and you can literally then use it just like a function. You can plot it like a function. You can get values of y at different values of x just like a function. So it's a very convenient way to give the result. And then the x vals could be values that you want the value of y at. So without this last line, you get back an interpolating function, which is that whole function. It's the whole spline, the entire spline. If you want, like in the MATLAB context, if you want for certain values of x, you want the values of y, then you could do this. You can do interp function, x vals, put in the x value or values, and it will return the corresponding values of y. And once again, there is an example in the Python tutorial. Everything I do in class and everything I ask you to do with built-in functions, there are examples of the Python built-in functions in the Python tutorial. Okay, this first point is what I just emphasized. It gives you the entire interpolation function, not just the values at a certain subset of points. Okay, so we're out of time. Any last second questions, minute questions before we adjourn? We'll pick this up on Thursday. We're going to talk about Fourier analysis. There's still a whole lot we can talk about in terms of curve fitting interpolation. I'm not going to go crazy, but I do want to show you how powerful this will be. So everything, is this true? Yeah, so everything for the rest of this chapter is not stuff I'm going to ask you to do, but it's stuff that I want you to be aware of that it can be done and that you know where to look to figure out how to do it. So we'll talk about Fourier analysis. We'll talk about what happens if you have multi-dimensional data. So rather than just y as a function of x, what if you have y as a function of x1 and x2, or x1 and x2 and x3? So 2D or 3D data, not just one. We'll look at a very interesting example using sunspot numbers. Turns out people have been keeping track of how many sunspots appear on the sun going back several hundred years. So it's a very interesting data set to look at and analyze. So we'll look at that from a Fourier analysis standpoint next time. Okay, so if you have finished problem set 2, right? Yeah. Oh, so you're all sitting around with nothing to do. So you can do problem set 3 if you like. Oh, due date. I'll email the due date. I haven't figured out when it'll be due. Friday is obviously probably too soon, so sometime next week. We're a little bit off of our Friday schedule. Anyway, so I'll email out the due date, but you can start problem set 3 if you'd like. Well, I'd encourage you to. And then on Thursday, we'll look at how we can extend these ideas to more powerful, and so we'll do some image analysis. We'll do the sunspot example. It'll be fun and interesting. All right, so I'll see you then.